Welcome to AI-powered project management, where machine learning meets practical delivery. This presentation shows how integrating AI into planning and execution can improve efficiency, generate predictive insights, and support strategic growth across portfolios. Think of this as a roadmap. We'll cover the algorithms, data pipelines, feature design, forecasting, and the enterprise enablers needed to scale AI responsibly in project organizations. This slide maps common AI techniques to real project use cases, showing how supervised learning drives more accurate estimation. Unsupervised clustering uncovers groupings of similar risks. Reinforcement learning improves dynamic scheduling, and deep neural networks enhance earned value forecasting. The point is that each algorithm has a practical role. Chosen and tuned correctly, they reduce uncertainty and turn historical patterns into actionable decisions. The data pipeline diagram highlights the journey from messy project records to model-ready training sets. Schedules, cost ledgers, issue logs, and external feeds are extracted and normalized, then cleaned to resolve inconsistencies and fill gaps before conversion into machine-readable formats. That transformation, automated ingestion, standardization, and feature packaging, is what enables reliable predictive modeling rather than one-off analytics experiments. Feature engineering is where domain knowledge really pays off, and this slide emphasizes crafting variables like float consumption rate, resource volatility index, and defect density momentum. Rather than relying only on complex black box models, thoughtful, domain-specific features translate into high-impact, actionable insights that leaders can act on. Early warnings for schedule slip, capacity bottlenecks, or emerging quality risks. Milestone forecasting uses regression models trained on inputs like past task durations, scope change counts, and team velocity to produce probabilistic, confidence-bound completion ranges. Instead of a single date guess, executives receive a likelihood distribution, most likely completion plus a 90% interval, so teams can quantify uncertainty, prioritize mitigation, and communicate more credible forecasts to stakeholders. Predictive cost modeling leverages gradient boosting on commitment logs, change order velocity, and commodity price indices to surface cost, overrun risk weeks ahead of traditional signals. The slide shows how AI processing generates early warning signals that feed contingency planning and scope adjustment decisions, enabling more proactive financial control and a measurable reduction in surprise budget impacts. Reinforcement learning agents are used to optimize resource allocation by simulating thousands of scenarios, iteratively learning constraints like skills, delivery dates, and contractual terms. The result is an optimized scheduling engine that minimizes overtime, respects constraints, and prioritizes cost-effective sequencing, consistently producing plans that outperform manual leveling in both schedule variance and overtime cost. Natural language processing automates team composition by semantically matching task descriptions to candidate CVs and talent repositories. The diagram shows an NLP engine converting requirements into recommended team lineups, reducing bench time, closing skill gaps, and increasing productivity. In short, semantic matching speeds assembly of the right people for the right roles, while lowering labor costs and improving time to start. Clustering algorithms sift decades of postmortem reports and historical records to surface emerging risk themes, supplier insolvency, regulatory shifts, or extreme weather, before they become crises. The output is a living risk register with monitor, assess, and plan statuses, giving project leaders a pre-human radar for threats, so mitigation can start earlier, and strategic resilience is strengthened. A Bayesian network approach moves contingency planning from rule-of-thumb buffers to dollar-by-dollar, probabilistic allocation. Identified risks, historical impact data, and project-specific vulnerability scores feed the model to infer reserve needs aligned with corporate risk appetite. The result is a defensible total reserve recommendation and a transparent trade-off between traditional flat allowances and data-driven buffers. Practical adoption follows phases. Start with descriptive dashboards for real-time status and historical baselines. Move to predictive alerts for risk identification and proactive notifications. Then advance to prescriptive optimization for automated recommendations and strategic resource allocation. Success depends on change management, solid data governance, and addressing ethical concerns like bias and transparency while building skills and pilot momentum. Finally, AI augments rather than replaces project judgment. Algorithms crunch data, identify patterns, and automate routine tasks, while humans provide context, ethics, and stakeholder nuance. That synergy delivers faster delivery, cost efficiency, and enhanced reliability, positioning early adopters for competitive advantage, but only when human oversight, responsible governance, and clear accountability remain central.